It's time for a review. We've covered a lot of information. Let's see what we remember and what we don't remember. And let's take all these little Lego pieces and start putting those Lego pieces together in a refrigeration cycle to build that bigger block of information. So we have a lot of stuff that we've covered. And if you look at this, that's too much to memorize. I don't want you to memorize it. There's some words that we have to memorize, but ultimately I want us to think about how the cycle works. And we look at things in individual pieces. By having this all written up here, I can refer to these little notes, but also it shows where all these things are attached to the refrigeration cycle. So as we go through this review, say the words with me, say them out loud. Try to say these words with me, because physically saying them out loud is going to help, but ideally if you're participating, it's going to help this stuff come through. Now some of the stuff you're already going to have down, we're going to go through the basic refrigeration cycle, and then we're going to add all these other pieces to it so we can see what it looks like. It's a cycle, so we can start anywhere in this cycle, but I like to start at the compressor because it's the easiest thing to find, and we send electricity to it to make this cycle start happening. So we have our compressor. It's also called a vapor pump, and what does it do? It sucks low pressure vapor, it pumps high pressure vapor, it moves the refrigerant. So all those things the compressor is doing. This horrible little symbol, don't think of that. Think in your mind a picture of a compressor. That's what I want you imagining in your minds. From there, we leave the compressor as a high temperature, high pressure, superheated vapor. The compressor raised the pressure. That line that it comes into has a very specific name. It's called a discharge line, compressor discharge, discharge coming out of. So coming out of the compressor. It's also called a hot gas line. The gas, the vapor in there is a gas. And if you touch it, ow, it's going to be hot because it's a hot gas line. And the state of refrigerant is a high temperature, high pressure, superheated vapor. What we need to do to that refrigerant is de-superheat it. We need to take it back down. We need to cool it down to saturation. So as we get into the condensing coil, we're still dropping heat. The very top little section of that condensing coil, the very top bit of that is still de-superheating it. It's a big number change, but it's a very little, small amount of BTU overall. Once we get it down to saturation, it's 100% vapor, but now it's at its saturation point, the point where it's going to change states. That's important. Now as this refrigerant starts to change state, it's giving up heat. It's rejecting heat. It's warmer than the air temperature. And as we reject the heat out of that refrigerant, it's going to be the same exact temperature all the way through saturation because it's latent heat. It's going to be changing state without changing temperature. So the refrigerant is going to be changing from a vapor into a liquid, rejecting heat, all that saturation. So here at the middle, we get them about 50% liquid, 50% vapor. We've changed about half of it from a vapor into a liquid, still the same temperature. And then we reject more and more heat and we get more and more liquid. Right here at the bottom, we end up at 100% liquid. Now it's still at saturation, but it's 100% liquid. It's 100% saturated liquid. It's still going to be warmer than the air temperature, so we can still reject heat. So we continue to reject heat out of it, and we start to subcool below saturation. Now subcooling, it's changing in temperature without changing state, so that's sensible heat. We've subcooled it below saturation. So here now we have our liquid line. It's not a saturated line, it's a liquid line, and really it's a subcooled liquid line. I like to refer to this line as a warm, high pressure, subcooled liquid. So when you touch it, to your touch, it's going to feel warm. If you touch the hot gas line, it's going to be hot, it's going to burn you. But this liquid line is going to be warm to your touch. But according to the gauges, it's going to be high pressure, the red gauge, high pressure. And according to the refrigerant, it's going to be a subcooled liquid. Even though it's red, red's representing the high pressure, not temperature, high pressure. So according to the refrigerant, this high pressure, it is still subcooled. It's subcooled below saturation. So this small line, that's a subcooled line. Then we had our liquid line filter dryer. Let's go over that. It's called a liquid line. It's called a liquid line because it goes where? I always get this confused. Oh yes, the liquid line. Notice it does not go on the hot gas line. It goes on the liquid line because it's a liquid line filter dryer. Two different names, filter dryer. It's filtering the refrigerant and also drying, absorbing H2O, pulling moisture out of that refrigerant. That's very important. That liquid line filter dryer can be anywhere on the liquid line, before the metering device, at the outdoor unit, or even inside of the outdoor unit, but it's still liquid. Inside of the outdoor unit, it's still the liquid line. Maybe it's very small, maybe it barely fits, but it's still going to be liquid. That's where our liquid line filter dryer is going to be. That arrow should be pointing away from the condensing unit and towards our metering device. From there, we end up at our metering device. In HVAC, we have two names, metering device, also called an expansion device. It restricts it from a high pressure liquid to a low pressure saturated mixture. So that low pressure saturated mixture is going to be important. It's restricting it. Now specifically, we got several different types of metering devices, several types of expansion device. We have a fixed orifice metering device, also called a fixed orifice expansion device. It's allowing for expansion on the other side, so it's still an expansion device. Then we have a thermostatic expansion valve. It's allowing for expansion on the other side, but it's a valve that opens and closes. We also have an electronic expansion valve, and we have automatic expansion valves and float valves and several other kinds, but most we're going to be talking about fixed orifice, and we're going to be talking about TXVs. So from there, a refrigerant's expanding. As it's expanding, it's a larger overall chamber. So we have more volume, and we also have a pressure drop. When we have a pressure drop, we also have a temperature drop. So that temperature drops. Well, now we had that 100% liquid. Some of that liquid, bam, flashes, immediately changes state from a liquid into a vapor. As it does that, it's absorbing heat, because every time a substance changes state from a liquid to a vapor, it absorbs heat. But what is it absorbing heat from? It's absorbing heat from itself. Adiabatic expansion, it's cooling itself back down. So it's not really a gain or a loss. And we write down 75% liquid, 25% vapor, but we know that's not true, and there's many different variables that affect what's happening and how much liquid and how much vapor we have. But that flash gas is how much flashed into a vapor instantly to cool the remaining liquid that's there. Now that liquid's going to be important. That liquid's going to be boiling from a liquid to vapor. The heat from the air is making the refrigerant boil, but also the refrigerant boiling is absorbing heat out of the air. If I take heat away from the air, what does the temperature of the air do? That's right, it starts to drop. So that refrigerant boiling is key. Notice it starts boiling from that metering device. Right there, it all becomes saturation. And boiling is a cooling effect. As a substance changes state from a liquid to vapor, it absorbs heat. It's a cooling effect. However, the word boiler was already taken, so we call it the evaporator, because evaporator is also changing state from a liquid to a vapor, so we call this the evaporator coil. The majority of this coil should be evaporation, and it's going to be latent heat. It's going to be changing state without changing temperature. So all of this saturated temperature will be the same temperature as long as there's liquid and vapor. Now, how much saturation is going to depend on that metering device. A thermostatic expansion valve is going to try to maintain the right amount of refrigerant for that evaporator, regardless of the conditions. If I have a fixed orifice metering device, my saturation could be right here, or my saturation could overfill and flood the entire evaporator coil. So that fixed orifice metering device has very little control, whereas the TXV is going to try to maintain this much superheat, which means this much saturation. And that saturation, that latent heat is so important. That refrigerant boiling, changing state, absorbing a massive amount of BTU, that is the key to refrigeration cycle. That's where we're getting the most heat. Now, after I boil that refrigerant completely into a vapor, it's now 100% vapor, it's still lower than the air temperature. The air is warmer than that vapor. So the heat still goes into the refrigerant. But now that refrigerant vapor starts to increase in temperature. It stays vapor, vapor to vapor, but now it's a warmer temperature. So changing temperature without changing state is sensible heat, measurable heat. And we add that as superheated vapor. I'm superheating that vapor. So we end up with our superheated vapor at the very top. Our thermostatic expansion valve measures how much superheat. With a fixed orifice, we still need to check superheat to see how much superheated vapor we have. And we have to use that chart or formula to find out how much we should have. We can't measure the saturation. But by knowing how much superheated vapor I have, I can see how much saturation I have. So if I got way too much superheated vapor, I know I got very little saturation. If I have too little of a vapor, I know I have too much saturation. So it gives an idea what's happening. And then after we boil it all to a vapor, we superheat that vapor, but it's still a low temperature, low pressure, and that suction line, it's going back towards that compressor. But the suction line is also called a gas line. It's also called a vapor line. And the state of refrigerant in that line is a low temperature. If you were to touch it with your feelings, it would be low temperature. The heat's leaving your hand, going to that refrigerant. It's a superheated vapor, but it's still low temperature, so it's absorbing heat still. That's why it's insulated. Also, it's going to be at low pressure. The blue gauge, the low pressure gauge, is measuring that. And according to science, the science of the refrigerant, it is superheated. So when you touch it, it's going to be low temperature, but according to the refrigerant, it is superheated above its saturation temperature. So we get that low temperature, low pressure, superheated vapor back into the compressor. And the compressor then takes it from low pressure back to high pressure. So some key components here. Let's go back and add a few little more vocabulary words that we've talked about. Let's review them again. Our superheat is superheated vapor, the amount of sensible heat added to a vapor above saturation. So here's saturation, and we added sensible heat above that saturation. It's very, very important how much sensible heat we've added above saturation. We have a formula for that. The formula is the actual suction line temperature. You can actually touch this line. You can put a thermometer on that suction line. Our formula is the actual suction line temperature. This is an actual line. You can actually touch it. You can put a thermometer on that line. So if we get the temperature of the actual suction line, we write that number down. Notice it's in degrees Fahrenheit. But also we have to get suction saturated. Suction saturated. Suction saturated is PSIG converted to temperature. So we get our suction PSIG and convert it to a saturated temperature. So we write that temperature down right there. Then we take our actual suction line temperature minus our suction saturated temperature equals our superheated vapor. So notice these are in a very specific order. The line temperature should be warmer than the saturated. Saturation is happening down here. The line temperature should always be warmer than that. So when you're doing your math, it's important to get the numbers in the right space. If you end up with a negative superheat, that's a red flag. We have something else wrong. Our instruments aren't right. We have a thermometer in the wrong spot. We're using the wrong temperature or pressure conversion. Something else is wrong. But when you're getting a negative superheat, that's something you want to look at. It's impossible to have a negative superheat on the suction side. We also have a little note here that we focus more on superheat with a fixed orifice. So it's a fixed orifice meter device, we look more at superheat. But still, with a TXV, we still want to check superheat. We want to see if it's doing its job. So we check superheat regardless of what kind of metering device, unless it's an automatic. An automatic is different. But with any other metering device, we want to check superheat. We just focus a little bit more on it when it's a fixed orifice metering device. So that's very important to understand. So now we understand superheat. By knowing how much superheat, I know how much saturation is in the evaporator. So over here, we then change it from a low temperature, low pressure superheated vapor up to a high temperature, high pressure superheated vapor. And there's really a formula for that. We don't use it much, but really it would be the actual discharge line temperature minus the liquid saturated temperature. Because remember, it's superheated above saturation. So now we're on the high side. We don't really typically do that number much, but it's important for us to understand it. So now we can look at a definition for desuperheating. Desuperheating, removing sensible heat from a vapor above saturation. So here we're taking that sensible heat away. Over here, this superheat's adding to the system, and over here we're taking superheat away. Over here, this was superheat added above saturation. I want to take superheat away. Why do I want to take superheat away? To get it back down to that saturation. So then we have our saturation, changing state. That refrigerant changing state is so important because it's dumping, rejecting, getting rid of a ton of BTU of heat energy. That's so critical for us to reject that heat. That's where the magic's happening. That's where the majority of that heat's rejecting out of there. So it's really important. Then after we superheat it, we change it from a vapor to a liquid. It's still warmer than the air temperature. We can now subcool it. We have a definition for subcooling. It's the amount of sensible heat removed from a liquid below saturation. Again, here's our saturation, subcooling it below that saturation. We also have a formula for subcooling. Subcooling is the liquid saturated temperature, PSIG converted temperature, liquid saturated temperature. So here's our saturation temperature, but we're going to get our red gauge, convert that to a temperature. Notice it's a temperature, degrees Fahrenheit, not a pressure. It's a conversion minus the actual liquid line temperature. We can actually touch this line, this small line. We can put a thermometer on there, a clamp thermometer, digital, and we can write the temperature of this line down. So we write the temperature of that line down. Then we have the liquid saturated temperature minus the actual liquid line temperature equals subcooled liquid. That's how much subcooling we have. So we can see if I only have a little bit of subcooling, I don't have enough liquid. If I have too much subcooling, I got too much liquid in my condenser. It tells us what's happening. It's a little bit easier to look at than superheat because it's already in a liquid. It's easy for us to measure. We focus more on subcooling if we have a TXV, but we still want to look at subcooling even with the fixed orifice. We still want to see what's happening with our subcooling. With a fixed orifice, we have a chart we're going to be looking at. But that's our basics of our cycle. Now, some other key words. The key word being saturation. This is a beautiful, beautiful word. Saturation is so overlooked in HVAC, and it's such an important word for us. So when I say saturation, ideally this is coming to your mind. If you don't remember anything else, just memorize this. Anytime somebody says saturation, immediately be thinking PSIG converted temperature. PSIG converted to temperature. Really, it's PSIG converted to a saturated temperature. Remember, we have the temperature pressure chart. It's also called a saturated temperature chart. These pressures are almost worthless. We need to take that pressure and convert it to a saturated temperature here, or we take this pressure and convert it to a saturated temperature here. So now I know what's happening. Even though I'm getting the pressure outside, it's telling me the saturated temperature of the majority of that evaporator coil. Even though I'm over here on the liquid line, I get that saturated temperature. It's telling me what's happening in the majority of the middle of that condensing coil. So that's really important. It also means boiling and evaporating. Is the refrigerant boiling? Is it evaporating here? Well, yeah, it should be. And is the refrigerant condensing? Over here, is it condensing, changing state from vapor to liquid? Absolutely, or it should be. And then also it means whether there's liquid and vapor both exist. Liquid and vapor. Is there liquid and vapor? Yes, changing state. It's boiling. Liquid and vapor both exist. Different percentages, but it's still existing. Over here, do we have liquid and vapor? Absolutely. There's liquid and vapor. There's different percentages as we go through, but there's still liquid and vapor. What about a recovery tank? We have liquid and vapor? Then it's going to be at saturation. A brand new tank of refrigerant, as long as you have liquid and vapor, it's going to follow the temperature pressure chart. PSIG converted temperature. They should match. The temperature of that tank and also the pressure, they should match when you convert it to temperature and pressure. That should be the number. The temperature of the tank at the bottom where the liquid is and the PSIG converted temperature, they should both match. It should be the same number. Also, change of state. Is refrigerant changing state here? Absolutely. Is refrigerant changing state here? 100%. And it's also latent heat, and that's what's so important, that latent heat. That changing of a state is what's so powerful. It's absorbing a massive amount of BTUs. And over here, it's rejecting a massive amount of BTUs. So that latent heat's important. So that one word, saturation, takes all that in. So suction saturated, blue, PSIG converted temperature, I write that number down here. And on the outside, my liquid saturated, PSIG converted temperature, I write that number down right there. It's saturation. It's a beautiful, beautiful word. It's fantastic. All right, so that's our basic cycle. Now let's take a look at a little bit more of what's happening. We know on the outside, my saturated temperature needs to be warmer than my air temperature to get heat to leave the refrigerant and go to the cooler air. So that's important for us to have the temperature difference. Now that temperature difference can be defined right here as condenser TD. TD being too different. It's also known as saturated temperature rise. So my saturated temperature has risen higher than the air temperature. It's also called saturated temperature over ambient. The air coming in is called ambient air, the ambient air around the condenser. So the saturated temperature has to be higher than the ambient temperature. Because the saturated temperature is higher than the ambient temperature, that heat's rejecting. By design, there's different numbers. Typically speaking, on your more modern residential systems, like after 2010 or after 2015, they're going to be about anywhere from 10 to 15 degree TD by design. So we know the saturated temperature should be about 10 to 15 degrees higher than the air temperature. So as your air temperature goes up, what's your saturated temperature going to do? That's right, it's going to go up. As the air temperature outside starts to drop, what's your saturated temperature going to do? Absolutely, it's going to drop. Let's also think about a tank of refrigerant. If I have a tank of refrigerant and I take it outside to where it's hotter, what's the pressure in that tank going to do? That's right, it's going to go up in pressure. Our compressor just raises it so many degrees above that. So that TD is how much we raise it above the saturated temperature. It's naturally going to go up in temperature because it's warmer outside. So then we just add a temperature difference to it. So let's say that we have a 15 degree TD and it's 80 degrees outside, we add 15, our saturated temperature should be 95 degrees. If it's 100 degree air coming in, our TD is then going to be, say, 115. We simply add 15 degrees to that. Every system's a little bit different, but typically the newer systems have a smaller TD and the older systems have a larger TD. Units in the 80s had a 30 degree TD. And it's also different for refrigeration. A lot of refrigeration systems, the older ones, had a 30 to 35 degree temperature difference. So the refrigerant was 30 to 35 degrees warmer than the air. Some of the newer refrigeration systems are a little bit more efficient. So sometimes now you're seeing a 15 to 25 degree temperature TD. The reason is that refrigeration has to be able to flood that condenser in the wintertime so that it can maintain a higher pressure. If you have these giant coils, it's going to take too much refrigerant to flood that condenser. Also space. With air conditioning, we have room to put that bigger condenser. In commercial and kitchens and all this, you don't have this space for those units, so they have to keep them small as possible. So a little difference in design, but still that TD is going to be important. How do we find TD? Well, I got a little formula for it. Our liquid saturated, PSIG converted to temperature. So now I know the temperature here. So my liquid saturated temperature minus the ambient temperature, or the temperature of the air coming in. liquid saturated temperature minus the air entering the condenser, and that equals condenser TD. So that's how we find it. We get that chart, we can look and see if it matches that. Now, the systems that are newer, remember they made larger condensing coils to get the TD lower. Older systems had smaller condensing coils, so the TD had to be higher. It's all about heat transfer. We're transferring heat by thermodynamics. It's going to be the temperature difference. So a bigger temperature difference will transfer heat faster than a smaller temperature difference. Also the type of metal we're using. So aluminum and copper transfer heat much faster than wood or rubber. And also for temperature difference, surface area, how big that coil is going to be. So that surface area is key. The newer systems, larger surface area. We can transfer heat a lot faster and also have a lower temperature difference. And there's also surface area can be considered with airflow. The more airflow moving across here, the more important that's going to be. And again, airflow, so critical. We hadn't talked about airflow yet, but if you're blocking airflow or you have a dirty condensing coil or anywhere you're not transferring that heat from, what's it going to do to your TD? Your TD is going to go up. Your temperature difference is going to go up. To get that heat to leave, we're going to have a higher temperature difference. So now instead of it being so efficient, it's being blocked by airflow, or the airflow is being recycled, or it gets dirty or whatever. That's causing a higher pressure to get the heat to reject faster. So that higher pressure is a whole lot more work in the system. So all that ties in together. So then we have the inside coil, where the inside and outside are opposite. The outside is going to be rejecting heat. The inside is going to be absorbing heat. The outside saturated temperature needs to be warmer than the air temperature. The inside saturation temperature has to be lower than the air temperature. The outdoor unit rejects heat into the air. The inside unit absorbs heat out of the air. A little bit more going on with our evaporator coil. So we're going to have our return air. The air is being sucked into that evaporator coil. So we're return air temperature, and then we're going to be having supply air that we blow out. The evaporator coil has a lot going into it. We want to sensibly cool the air, so we need to have heat transfer. So the temperature of the air is going to be warmer than my saturated temperature. So heat's going to leave the air and go into that cooler refrigerant. So the temperature of the air is really going to drop. You're going to see a temperature drop in the air. But also, we want to dehumidify or pull moisture out of the air. That's critical. That dehumidification is critical. How we do that is we're going to have our saturated temperature lower than our dew point temperature. So now we're making that moisture condense, the dew point, where it's condensing from a vapor in the air to a liquid. That liquid collects on the evaporator coil, and we physically drain that liquid outside. Because it's changing state from a vapor in the air to a liquid that we're draining outside, that's called latent cooling. We're literally taking moisture out of the air to lower the humidity. So that latent cooling is important. Understanding that our saturated temperature has to be below the dew point temperature for that to happen. Place like Las Vegas, you're going to have mainly sensible cooling. Most of the time, you're having no latent cooling at all. In a place like Florida, you're going to have a significant amount of latent cooling. In some places, you end up with the weather's pretty nice, but the humidity's high. In places like that, you need dehumidification, which is only latent cooling. Temperature of the air is great, but you need to pull the moisture out. Understanding that our evaporator coil is doing all that is so important. So as we take moisture out of the air and we take heat out of the air comes back out, mixes with the whole rest of the house, and we start cooling the house off. By taking heat out of the air, the temperature of the air inside starts to drop. It's a whole connection. We don't destroy heat, we don't destroy energy. We simply take the heat from inside and we reject that heat over here to the outside. So that's what's happening in the refrigeration cycle. But the airflow is going to be critical. The airflow plays a huge part in that. So we also have our temperature difference in that as well. The TD, the temperature difference between the air and that refrigerant, TD. So most of the time, our TD is going to be about 35 degrees, depending on airflow, massively important, and also how much dehumidification we're going to need. But TD is the difference between the air and the refrigerant, two different. So that temperature difference is going to be important. How do we find our TD? Well, we take our return air temperature, temperature of the air coming in, minus our suction saturated, suction PS. Let's see how we're going to find TD. I'm going to need my return air temperature. So regular temperature of the air coming into the evaporator coil, return air temperature. And then I'm going to need my suction saturated. Suction, PSIG, converted to a saturated temperature. Return air temperature minus suction saturated temperature equals evaporator TD, evaporator temperature difference. And again, it's typically 35 degrees. So the saturated temperature should be approximately 35 degrees lower than the air temperature. And we say approximate because there's a lot of things that go into that, a lot of variables, especially in air conditioning. Refrigeration is a little bit more stable. Typically with walk-in coolers, walk-in freezers, there's about a 10-degree temperature difference. And we have reach-in systems, it's typically about a 20-degree temperature difference. So in residential systems, because we have an adjustment of airflow and humidity, that TD is not set in stone. So we typically say a 35-degree TD plus or minus 5 kind of gives you a window or a range, but it's not a set in stone thing. But it gives you importance. TD, 2 different numbers. So now we can also see that as we took a tank of refrigerant and we brought it inside of the house, that lower temperature acting against that refrigerant would give us a lower pressure. So just by having a lower temperature, we're going to have a lower pressure. As we took that temperature of that tank and warmed it up, like say a warmer house, we'd have a higher amount of pressure. So as we have a higher amount of temperature of the air coming into that evaporator coil, we're going to end up with a higher saturated temperature and a higher suction pressure. As we have a lower temperature of the air, we're going to end up with a lower saturated temperature and a lower suction pressure. So the temperature and the pressure go hand in hand. That compressor is ideally bringing it so many degrees lower than the air temperature though. So that temperature difference is how much lower the temperature is of the refrigerant where it's boiling compared to the air temperature. When you're setting outdoor TD and indoor TD, how that temperature difference affects the pressure, let's also look at something else we talked about, which being compression ratio. If I have a higher indoor temperature, I have a higher suction pressure, and if I have a lower outdoor temperature, I have a lower discharge pressure. So my refrigeration cycle is a very low compression ratio. I'm absorbing low pressure vapor, pumping high pressure vapor. It's very easy to move a lot of refrigerant. And where's the heat located? Our heat is in the refrigerant. So if we're moving a lot of refrigerant, we're moving a lot of heat, and we call that capacity. So a lower compression ratio gives us more capacity to move more heat. Imagine if you were moving boxes very close, we're able to move a lot of boxes. On refrigeration, we're able to move a lot of refrigerant very quickly. That gives us a high capacity. Our heat is located in the refrigerant. So being able to move a lot of refrigerant means I'm moving a lot of heat. As our outdoor temperature rises, our head pressure has to rise. It has to rise above that. So to maintain that same amount of TD or temperature difference, to get that higher saturated temperature, I have to have a higher pressure. So that compressor has to pump it up to a higher amount of pressure. So now taking these boxes and moving them up, that's more motion. You're going to have to move less boxes overall. In refrigeration, we're moving less refrigerant, which means we're moving less heat because that higher compression ratio. Now, as my indoor temperature drops, to maintain that TD, that temperature difference between the refrigerant and the air, I also have to have a lower saturated temperature. To have that lower saturated temperature, we have a lower suction pressure. So now that compressor is having to go down here low to grab that vapor, and then it's kind of to push it up high here. So if you're moving boxes, it would take you longer to move boxes because you have to have more motion between the low and the high. Compression ratio is very similar to that. We're having to suck in low pressure vapor, pump at the high pressure vapor. That's a bigger compression ratio. Overall, that means we're moving less refrigerant. By moving less refrigerant, we're moving a whole lot less heat energy. Moving less heat energy means we have lost capacity. We don't have as much capacity of cooling as we did before. So that's a big effect on the refrigeration system. The suction side is more critical than the high side. As that suction pressure drops, we also end up with less density of that vapor. That vapor is more spread out. So it's not only we're having to reach down low to grab that suction pressure, we're also having to collect it all together because it's not very dense. So I'm collecting all this low pressure vapor and then having to squeeze it together to push it up high. It's a lot of work, and have the issue of oil. I'm not getting the oil return like we should. So there's a lot of factors. Also, if you block airflow and you have a dirty evaporator coil, you're magnifying that even more. Your suction pressure is going to drop even more, which is even more work on the compressor. So that compression ratio really affects the capacity. Now, if we want to find our compression ratio, we need to know the difference between our suction side and the high side. But we have to take into account something else. Do you remember? We have to take into account our atmospheric pressure. So I'm going to take my head pressure and add my atmospheric pressure. Now for test purposes, we just use 14.7. So my high side discharge pressure plus 14.7 equals my PSI absolute. Same thing with my suction. Get my suction pressure, add my true atmospheric pressure for test purposes, 14.7, and get my PSI absolute for my suction. And then I take my discharge PSI absolute divided by my suction PSI absolute, and that gives me my compression ratio. And the lower your indoor temperature is and the higher your outdoor temperature is, the bigger your compression ratio is going to be. The more work you're going to have on that compressor and the less heat you're able to move, the lower capacity you have. Also think about walk-in coolers and walk-in freezers. They're going to have a bigger compression ratio, especially a walk-in freezer. It's having to go really, really low up to really high. But they design those systems to work like that. So they design the compressors to have the oil return like it needs. We add different accessories on the system to be able to handle that. The compressor motor has a much bigger horsepower motor compared to its BTU capacity. On residential AC, we typically have a 1 horsepower motor to a 1-ton refrigeration pump. But when we get into refrigeration systems, we end up with larger horsepower motors compared to those tons of cooling, tons of BTU that we need to make this heat move. So it all ties in together. It's all very important. So if we bought a 2-ton system, a 24,000 BTU capacity per hour, that's only going to be at AHRI conditions. In other words, an 80-degree return air temperature at 50% relative humidity and a 95-degree outdoor day. As the temperature goes higher and the temperature inside goes lower, you end up with a higher compression ratio, which means you have less capacity, less ability to move heat. See how it all ties together? Now, let's take a look at Delta T. Remember, Delta means the same media. Let's look at Condenser Delta T. The temperature of the air coming in versus the temperature of the air coming out. I've had students before ask, well, how do I find where the air is coming in? Take a piece of paper where it sucks into the unit, that's air coming in. And if you put it on top and it's not staying, it's just coming out, it's just blowing away, that's air coming out. So we get the temperature of the air coming in and the temperature of the air coming out, that is Condenser Delta T. Now that number is interesting because later we're going to be talking about airflow and we can find out from the manufacturer how much CFM of air they're moving. And if we know exactly how much CFM of air we're moving, there's a way to calculate with Delta T of the condenser how many BTUs of heat energy we're moving. Because it's putting all of the heat rejected just simply into the air, we can really calculate that. Now we're a ways from getting there, but it's really cool to know that we can calculate the BTU capacity of an air conditioner by how much heat it's coming out with the Delta T and knowing how much CFM there is. That's really cool. Now let's take a look at Evaporator Delta T. Let's look at the formula. Formula is return air, the air returning to the unit, where your filter's at, minus the supply air temperature, the air coming in the ductwork, the air going back into the house, equals Evaporator Delta T. It's air in versus air out. But let's notice something. It was degrees Fahrenheit of air coming in and degrees Fahrenheit of air coming out, which is a sensible heat number. But we know the evaporator coil doesn't just move sensible heat, it also removes latent heat. It's actually pulling moisture out of the air and draining that out as well. What's not taken into account anything to do with that latent heat. So this is what's interesting. Think about if you have a very humid climate. We're using some of the capacity, some of the BTUs of energy that I can move to dehumidify the air, to make that moisture from the air change state from a vapor to a liquid. And it takes a good amount of BTUs to make a substance change state from a vapor to a liquid. I got to pull a lot of heat out of that moisture to get that moisture to condense, collect on the evaporator fins to make it drain outside. So as I'm using capacity of my system to dehumidify, to pull moisture out of the air for that latent cooling, I end up with less BTUs of heat energy to change the temperature of the air. So if you have a more humid day, you're going to have a smaller Delta T. What about if you have a very dry day? Let's say we're in Las Vegas where there's no dehumidification whatsoever. That means we're using our entire capacity just to change temperature alone. So we could end up with a very high number of Delta T. In other words, we're spending all of our capacity just to take heat out of the air sensibly. You'll see a higher Delta T. But wait, there's more. What about airflow? Let's think about airflow. It's so critical. If I have a slow amount of airflow, the air is moving very slowly across this evaporator coil, there's a lot of contact time between the air and the evaporator coil. It has a lot of time to absorb heat out of the air. So as we're taking the heat out of the air is coming out much colder or less heated. So our Delta T will be very large. On the other hand, if I speed my airflow up, I'm moving the air across it very, very quickly. So the air doesn't have time to change temperature. So by having more airflow, I end up with a smaller amount of Delta T. That means that I'm still absorbing a heat BTU, but I have very little time to change the temperature of the air. So airflow alone is going to have a huge impact in Delta T, and humidity is going to have a huge impact of Delta T. But wait, we were talking about capacity, having capacity to make this happen. Does our capacity of our systems change? Yes, our capacity does change. We talked about our compression ratio, and the more work that compressor has to do, the less capacity. So let's think about this a little bit differently. As we're moving heat, the heat energy is in where? It's in the refrigerant. So as I have a higher outdoor temperature, I'm having to raise that pressure up a whole lot higher. My compression ratio grows. Because I'm doing all the work lifting it up, I'm moving less refrigerant, which means I'm moving less heat energy, which means I have less capacity to deal with. So that's going to affect my delta T. The outdoor temperature is going to affect my delta T. Also, the indoor temperature as well. As the indoor temperature gets lower and lower, that compressor is having to really dig down to gather up that low density vapor. As it's having to really dig down, that affects the compression ratio. So having a lower indoor temperature means I have less capacity to work with. So a high outdoor temperature and a low indoor temperature, I end up with even less capacity to work with. So the capacity of the system is going to affect my delta T. Plus, the coil size is going to affect it as well. Different size evaporator coils play a part in how much our delta T is going to be. There's a lot of variables. Is there a way to know what your delta T should be? And the answer is yes, absolutely there's a way to find this. The manufacturers publish some information called a performance chart. And what you need to know is the outdoor model number of the system. And then you match it with the indoor model number of the system. So now the manufacturer knows what you're dealing with. The manufacturer also wants to know how much CFM. We haven't measured airflow yet, but we need to know how much CFM of airflow is going through that evaporator coil, because we talked about that being important. So once you know those three factors, it also wants to know the outdoor temperature, because that's going to have an effect on capacity, and it wants to know the indoor temperature and the indoor wet bulb. Sometimes it just wants to know wet bulb, but with that, it knows the compression ratio, it knows the capacity, and it also knows the humidity you're dealing with. With those numbers, it can tell you exactly what your delta T should be with those conditions, which I think is cool. We can fine tune it. It should be exactly this. And I'm not getting that. Let's look for some other problems. But it takes time. We don't do that in every call. It takes a lot of work looking all that up, finding the numbers, and making sure we can find that table. So we don't do that a lot, but we can, and I've done it many, many times. But I don't do it every single call. It's a ton of time wasted. What's important to know is that we can find what it should be. But those numbers vary. There's a lot of different factors going into what that delta T is. Now the reason I'm telling you that, just like we talked about before, I can't say this enough, you're going to meet people that think there's one number for the delta T. Don't argue with them. I find that these people believe that delta T is like a religion, and they will fight to the death about it. They don't want to hear about the science or the math or anything else with it. They just want to go to what they were told, and that's the only number they want to hold on to. But over time, you're going to see that delta T number is going to be changing. It's not a set in stone number. Don't argue with them. Don't go to them and say, well, Ty said you're wrong. Just nod your head and go on. So that delta T changes. It's not a set number. So it's definitely a number we want to look at, but it's not a set in stone number. But there's another delta T that we have to work with. The other delta T we're working with is the delta T on our filter dryer. We get the temperature of the refrigerant going in versus the same refrigerant coming out, the same media. So the refrigerant coming in versus the refrigerant coming out. What do you think the delta T should be across that filter dryer? Well, the delta T really shouldn't be any. There shouldn't be any delta T. 1 degree I'm okay with. Once I start seeing 5 degrees of delta T across that filter dryer, that means there's a temperature change, which means there's also going to be a pressure change. So this is where I want to bring this up to the customer. I let them know that we're starting to have a restriction inside that filter dryer and let them make the decision if they want to go and make that repair or if they want to wait. And also we document that on the invoice. So if that pressure drop causes a problem somewhere else, we've documented it to that customer. Every technician seems to have their own idea. It should be this, it should be that. Here's how you know. If you look up the filter dryer brand, it'll tell you what temperature drop they should have on there. Also, some manufacturers for the equipment say your temperature drop is more than X, Y, or Z, then you need to replace it. So that's how you know. Refer to the manufacturer's instructions. So if I only had 3 numbers of a system to deal with, I don't want to know superheat, subcooling, and CFM of airflow. With those 3 numbers, I have a much better idea what's happening over all of this other stuff. It just gives me an idea what's going on. These other numbers are important. They're great to have. But let's go back and look a little bit more at superheat and subcooling. So we know our formula for superheat is the actual suction line temperature minus the suction saturated temperature equals our superheated vapor. I can get superheat coming right out of the evaporator coil. That's called evaporator superheat, and some manufacturers go by evaporator superheat. So if you're in tech support and they say, what's your evaporator superheat, they're warning the temperature of the actual suction line at the exit of that evaporator coil. It's also important when you're working with thermostatic expansion valves. The TXV is going to have a sensing bulb here and an extra tube here. It's monitoring superheat. So if you're going to adjust that TXV, seeing what superheat that TXV is seeing is also going to be very important. Most of us get our superheat over here at the unit because this is where our gauges are going to be, so we get our suction line temperature here. Are those temperatures going to be the same? Well, it depends. If we have a very small system, a short amount of suction line, the temperature here and the temperature there is going to be almost identical. However, if we end up with a very long suction line, we can end up with a much higher amount of superheat here. The reason is that line is cool. It's still absorbing heat. Heat from the air is going into this line and it's raising the amount of superheated vapor. So by the time you get over here, we've added or gained superheat. That means we have to then reject the heat back out. Sometimes if we have longer lines, we put thicker insulation on this to better insulate it, to better protect it. But these are some things you can look for. Superheat here versus superheat here. So if you're trying to adjust the superheat over here at this point, when in reality it's reading the superheat here, you see the conflict or some of the differences? So that's where we have superheat. Evaporator superheat and system superheat. But wait, there's another superheat. We also have superheat here as well. We can get the actual discharge line temperature minus the liquid saturated temperature, and we can read how much superheat is here. Can you think of what the superheat difference is going to be between here and here? It's going to be much higher. The reason it's going to be higher is the heat of compression and also the heat that we're absorbing from that motor. Remember, we're using the refrigerant to cool that motor. So we're going to be putting heat from that motor into the refrigerant as well. So the refrigerant coming out, the superheat is going to be a whole lot higher. On commercial systems, I like to calculate superheat here as well. I'll get the superheat coming in and also the superheat coming out. It's not a number that a lot of people use, but I want you to understand that it is a number and it does have some importance. So when you're talking about total system superheat, that's really where that's at. Now, a lot of times when people say total system superheat, they're really talking about it here. So you want to make sure you clarify total system superheat meaning discharge or total system superheat meaning at the inlet of the compressor. That way you know what they're talking about and you can communicate well. But also, even more important is the temperature of this line. Notice I got degrees Fahrenheit here. Why is the temperature of that discharge line going to be important? Can you remember what that temperature should never exceed? That number is 225 degrees Fahrenheit. Now, why should it not be above 225 degrees Fahrenheit? Well, that's because if it's 225 here, the temperature will be even warmer there. And in short, if it gets too warm in here, we're going to have oil breakdown. Oil is going to be breaking down. And we don't want oil breakdown. You don't want me breaking down either. There should be no breakdown. So if we keep it under 225 on the discharge line, I mean, it's going to be under the 300 whatever threshold it is inside the compressor, and the oil won't be breaking down. And it will be good shape and it will keep lubricating. Remember, if that oil starts breaking down, we're going to end up with no lubrication for our vapor pump. And imagine running your car engine without oil. It's not a good day. Not a good day at all. So we look for 225 degree discharge line temperature max. Now let's take a look at our subcooling. We typically get our subcooling at the exit of our condensing coil. So our subcooling is typically going to be here, subcooled liquid. Now there's also another number we can get subcooling from. We can also get subcooling right here before our metering device. Still on the liquid line, but we can get subcooling here. Now why do you think that would be important? Well, if we think about it, let's say if I had 10 degrees of subcooling here and ended up with 0 degrees of subcooling here. 0 degrees of subcooled liquid means I'm at saturation, which means I have saturation coming into my metering device, which means my metering device is only meant to meter liquid refrigerant. So if I have saturation, it's not going to work right, which is going to throw everything off on my superheat side. So I want to always make sure I have liquid refrigerant coming into my metering device. So by checking my subcooling here and making sure that I have at least 2 degrees of subcooling here, I know that I have liquid refrigerant entering my metering device. Now, if I'm losing subcooling from this point over here to this point, I can be looking for things like, where is this liquid line going? Is it in the attic? Is it absorbing heat? Is the attic warmer than this line and the heat from the attic heating that line back up? And if that's the case, we can insulate that line. So if we insulate that line, I can maintain my subcooling all the way to this point. Also, maybe there's some other mechanical thing that's close that's causing a problem. So these are things you can look at. Now remember, if we're working with a commercial system and we have a liquid receiver, that liquid receiver is going to change it. We're not going to look at subcooling with a liquid receiver. We're going to look at our sight glass, make sure we have a solid column of liquid. There's a lot more that goes into charging, not just the sight glass. I want to make that clear. We'll talk about that when we get to refrigeration, just to make sure you're working with somebody with commercial and they're not doing subcooling. That's why. So there's more that goes into it than that. Also, it's best if we have a sight glass right here before a metering device. I really don't care if I have solid liquid over here. I want to know that I have solid column of liquid going into my metering device. So in a perfect world, I would have a sight glass right here, but it's not always available. So again, if you have a liquid receiver on a commercial system, you're not going to be having that subcooling you're working with. Now, if you don't have a receiver, subcooling all day long. So subcooling is going to be important. So I got subcooling here and subcooling here. We don't typically check this one unless there's an issue. It'd be nice, but it's not always practical. If you're having a problem with the system, you can check subcooling there and help you diagnose some things. All right, let's take another step deeper in with that superheat and subcooling. Now, if I only had 3 numbers to work with, I'd want superheat, subcooling, and CFM of airflow. So let's take another look at superheat. So if we talk about superheat, let's focus first on our fixed Orifice metering device. We know that if we have a fixed Orifice metering device, we're going to focus more on superheat, or at least superheat first. What should that superheat be? We're going to need what we call target superheat, what it should be at. And to find our target super, we're going to need the return air wet bulb temperature. Wet bulb takes into account sensible heat and latent heat in one number. We're also going to need to know the outdoor dry bulb temperature. And we're going to put that number with the chart, or with the formula, or with the app. And that will tell us what our superheat should be. Now, there's a huge range. It could be as low as 5 and be operating good, or as high as 40 and be operating good. Why does it want those 3 numbers, and why is it affecting it? Let's think first that fixed Orifice metering device is just simply a fixed hole, a fixed bore, a piston, some people call it, but it's a fixed size hole. That fixed size hole sounds simple, but it's actually fairly complex in how it makes everything else work. So a simple metering device can be more complicated. Let's look at scenario number 1, the outdoor temperature. As the outdoor temperature goes up, there's more pressure on the high side. So I have a solid column of liquid with more pressure pushing against it. That fixed hole, what will happen? Well, if I got more pressure pushing against the liquid, I'll end up with more liquid coming into my evaporator coil. On the other hand, as my outdoor temperature drops, I end up with less pressure. I have less pressure pushing on that liquid. I end up with less liquid in the evaporator coil. So we got 2 scenarios, more liquid and less liquid. Let's compare it to something you can relate to at home. Let's say that we have 2 pans and we put both pans on the stove, and we set both stoves in the same size burner to have the same amount of BTUs of heat energy. And we have one pan with just a little bit of liquid in it, and we have the other pan with a whole lot of liquid in it. And we put them on, and they're both boiling. They're both going to be at 212 degrees Fahrenheit. But eventually, one's going to run out of water first. Which one's going to run out of water first? The one with less water in it. It's going to boil away first. The one with more water is going to take longer to boil away. So let's apply that to our refrigeration cycle. So let's see, if we have a lower outdoor temperature, we have less refrigerant in our evaporator coil. Well, that same amount of heat would make that less refrigerant boil away pretty fast. So we'd have our saturation would be way down here, which would mean all of this would be superheated vapor. So we'd have a very high amount of superheat. But if our outdoor temperature was higher, we're pushing more liquid refrigerant into our evaporator, so we end up with a lot more liquid. The heat can't boil all that liquid away fast enough, so the refrigerant would be here overflowing or even filling up that evaporator coil. So the outdoor temperature has a factor on what our superheat's going to be for that evaporator coil. But also, there's another factor. The temperature of not only the air, but the humidity coming into that evaporator coil. That's going to affect how fast that refrigerant boils away also. So let's look at this another way. Let's use that pan scenario again. Let's take 2 pans, and let's take the same amount of water in both pans. And we'll put them both on the stove. And we'll turn them both on where the water is boiling on both of them. But one is turned down just enough to where the water is boiling. So it's still boiling, but the other one is turned up all the way to where it's boiling fast and violently boiling. It's cranked up all the way. They both started out with the same amount of water in it. What would happen to the 2 pans? Well, the one that's cranked up highest, it's going to boil away faster because there's more heat energy making it boil faster. The other one that doesn't have as much heat energy will still be boiling, but it's boiling a whole lot slower. It takes longer for it to boil away. So let's use that heat energy aspect on this evaporator coil. So if we have more heat acting on this evaporator coil, the refrigerant will boil away very fast. So we could end up boiling all of our refrigerant away down here at a very small amount with a high amount of superheated vapor. On the other hand, if I have a very small amount of heat energy coming across this evaporator coil, I could end up with not boiling that refrigerant away, and I could flood my evaporator coil because the refrigerant is not boiling away before it exits the evaporator coil. Now if we add the varying pressure outside, let's say we have a hot day and there's a whole lot of pressure pushing a lot of refrigerant in, and the customer kept their indoor temperature down very low, we could end up very easily overfilling our evaporator coil completely. Saturation would overfill and we'd have saturation on our suction line. Notice it's a vapor line, not a saturated line, and we'd get a saturated mixture of liquid and vapor coming back to our vapor pump. Well, notice it's a vapor-only pump, not a liquid and vapor pump. So what's going to happen to that pump? It's going to start damaging it. It won't kill it right away, but that refrigerant coming in is going to start taking the life away from the compressor. That liquid refrigerant hitting the windings is going to start causing the insulation to come off those windings. It's going to start washing the oil away from the bearings of the compressor. That liquid getting in there is going to start doing damage against the valves. It's going to start doing damage against the compression side. It's going to start wearing and taking life away from that compressor. So we don't want that to happen. Typically, we want to make sure our suction line never drops below 5 degrees of superheat to protect that compressor. But with a fixed orifice, there's no way to control that. Let's take another scenario. Our outdoor temperature is low. There's less pressure. There's less pressure pushing that liquid through that fixed hole metering device. So we end up with just a little bit of liquid refrigerant here. And maybe the indoor temperature set a little bit warmer, and that heat coming across that evaporator coil is making that refrigerant boil away very quickly. Our saturation could be right here. We could boil all that liquid away from a liquid to vapor very, very quickly. And if we do that, all of this is going to be superheat. So I could end up with a superheat of like 40 degrees. We know that saturation is where we're absorbing most of the heat. So if I'm only absorbing heat right here, all of this being superheat, that's very little heat I'm overall absorbing. Now this high amount of superheated vapor coming back to the compressor may not be cool enough to cool the compressor. On top of that, the compressor raises the superheat from in to the superheat coming out. It raises that superheat up. As we raise that superheat up, my discharge line temperature could exceed that 225 degree temperature that we look for. So see how that all connects together? So even though it's a very simple metering device, it has a huge effect on our compressor. So if there was only a way, to maintain how much refrigerant was in that evaporator, if there was a way to control the right amount of refrigerant for that evaporator, regardless of what the outdoor temperature does, regardless of what the indoor temperature does, if we could open and close to maintain the correct amount of saturation in that evaporator, if there was only a way. Oh wait, you know what, there is. And Willis Carey even used it long time ago. It wasn't the first valve he did, but he finally realized we need a way to control it. So Sporlan used a thermostatic expansion valve, and this thermostatic expansion valve fit right here, and it had a sensing bulb measuring the actual suction line temperature and another line come over here measuring the suction pressure. With that TXV, thermostatic expansion valve, could measure the superheat. And if I kept this much superheat, I knew the majority of that evaporator coil was going to be at saturation, where we're absorbing a massive amount of heat. That B2, that latent heat, is so important. And by keeping this amount of superheat here, I know that if I have superheated vapor, I protect my compressor. Man, how cool is that? A thermostatic expansion valve solves all of those problems. The problem with the thermostatic expansion valves is they're getting abused all the time. These poor valves, people overheat them with a torch when they're putting them in here. People overheat the torch on the suction side where the bulb is. They damage these parts. They also don't keep it clean. Here we have our filter dryer before the metering device, but they'll let trash get in here and it clogs them up. They don't pull a good vacuum. You get acid in there eating them up. You get shavings from the copper in there that clog them up. They also don't braze while purging nitrogen, and you end up with oxidation inside of there, and the oxidation clogs them up. So they're abused beyond their capabilities. But if you do everything you're supposed to, these thermostatic expansion valves will last a lifetime. I've seen them 30 years old, still operating. Compressor's been changed out several times, same exact thermostatic expansion valves. Also got to make sure you also got to protect those tubes that's going over to the suction side. Make sure they're not rubbing a hole in anything. But these thermostatic expansion valves are great. They really work well. It's like cruise control. No matter what's happening, it opens and closes to keep the right amount of superheat under a typical set of conditions. It's not magic. It has its limitations that it can work with, but it's a great metering device. Now that we understand the importance of that thermostatic expansion valve, let's compare the different types of target. So target superheat for a fixed orifice. I need a return air wet bulb, outdoor dry bulb with the chart, the app, or the formula. Target superheat for a thermostatic expansion valve is going to be one of two things. Either what the manufacturer says on a non-adjustable, and it's not easy to find, but if you go through the manufacturer's information, it'll tell you. And also we have adjustable. That's my favorite. I want to be able to adjust it. And I can adjust these anywhere from 8 to 18 degrees of superheat. And I can set the superheat what I want it to be at, which is fantastic. It's great. But also we need to look at our target subcooling. Target subcooling for a TXV is more important, but it's also easier to find. Most of the manufacturers put it on the tag of the outdoor unit. So if we know what they want for subcooling, we can measure our actual subcooling. Liquid saturated temperature minus the actual liquid line temperature is a subcooled liquid. And we see, is our actual subcooling above, equal to, or below what the manufacturer wants? Target subcooling for a fixed orifice varies. As the day becomes hotter, our subcooling gets less. As the day outside is cooler, our subcooling gets higher. So that's why we use this chart to measure the outdoor temperature to find out approximately what our subcooling is for a fixed orifice. Again, fixed orifice, we focus more on superheat first, but then we still want to take a look at our subcooling. With a TXV, we want to do our subcooling first. Make sure that we're feeding that metering device enough subcooled liquid. If I'm giving enough subcooled liquid, I know it's going to check our superheat for us. But then I don't just want to assume that it's checking superheat. I want to actually measure, get my actual suction line temperature minus my suction saturated temperature equals my superheated vapor, and I compare that with what I want. And typically with a TXV, anywhere from 8 to 18, depending on the manufacturer. So that's how we use our targets to see where we're at, what we're doing, what we want versus what we want to be at, what we want versus what we're at. Now that we know how to establish whether it's a TXV or a fixed orifice, we can find out our target superheat, what we want, what we should be at. Then we can find our superheat, the actual suction line temperature minus the suction saturated temperature equals a superheated vapor. And we can compare those two. So if my superheat is too high, in other words, what I get is too high compared to what I want, we call that a starved evaporator coil. In other words, I want this much superheated vapor, but I have this much superheated vapor. So if I got too much superheated vapor, I don't have enough saturated liquid mixture. I don't have enough refrigerant inside of my evaporator coil. So that's one of the things we want to know. One of those numbers is going to be very important. Let's also look at another scenario. What if my superheat was within 3 degrees of my target? So I wanted this much superheat, but I was within 3 degrees of my target, of what I wanted. We'd call that good, fantastic, no problem. But what if my superheat was too low? So I wanted this much superheat, that was my target. But when I did my math, my numbers were too low. I only had this much superheated vapor. So if I didn't have enough superheated vapor, that means I have too much saturation or too much refrigerant in my evaporator coil. We'd call that a flooded evaporator coil. So you kind of look at that opposite. We're measuring superheat, but we need to know how much liquid's in there. So high superheated vapor means not enough liquid. We have a starved evaporator coil. Low superheated vapor, not enough vapor, means too much liquid refrigerant. There's too much refrigerant in that evaporator coil. Let's take a look at subcooling. This one's a whole lot easier. So subcooling, I have high subcooling. My subcooling is higher than my target. That means my target's this much subcooled liquid, but I have this much subcooled liquid. High subcooled liquid means too much liquid. We have a flooded condenser. If my subcooling is within 3 degrees of my target, we call that good. What if my subcooling is too low? I wanted this much subcooling, but only have this much subcooling. We would call that a starved condenser. There's not enough subcooled liquid in that condensing unit. So we don't just look at one side or the other. We want to look at both. So I got a flooded, starved, or good condenser and a flooded, starved, or good evaporator. Now, a lot of times you're going to have simple scenarios. So by converting high and low to starved or flooded and high and low to starved or flooded, it really makes things easier. Let's look at it this way. I have low subcooled liquid and high superheated vapor. That gets kind of confusing. But if we convert that to I have a starved condenser and a starved evaporator, that makes more sense. I don't have enough refrigerant here and I don't have enough refrigerant there. Most likely there's a leak, add refrigerant to the system. So we find the leak, add refrigerant to the system, and we're good and ready to go. Let's say we have a fixed orifice and I have a flooded condenser and also I have a flooded evaporator. That means there's too much refrigerant here and there's too much refrigerant here. We're overcharged. We need to recover refrigerant. What if we had this scenario, a TXV, and I had the right amount of refrigerant in my evaporator coil, but I had a flooded condenser? Well, in that scenario, it would also be overcharged. That TXV is maintaining superheat for us. Somebody put too much refrigerant, we need to recover that excess refrigerant out of there. That would give us a balanced charge, the right amount here and the right amount there. Let's look at another scenario though. What if I ended up with a starved evaporator coil and a flooded condenser? Now we're out of balance, but we know the refrigerant is supposed to leave the condenser and flow to the evaporator. So if there's too much here and not enough over here, then we have an imbalance. We have usually a restriction. The refrigerant's not getting from here to here. It could be a kink, something in the line, clogged up filter dryer, clogged up metering device, clogged up screen, but the refrigerant's not getting from there to there. Could be the wrong size or improper operating metering device. But these are things we look at. Also, non-condensables can cause that same scenario. Now here's what's important. If I only looked at superheat, I would say, hey, there's not enough refrigerant, and we'd be adding more, but we'd be flooding this even more. See why it's important to look at both sides. Now let's look at another scenario. I have a starved condensing coil, but I have a flooded evaporator coil. This one's a little bit more rare, but we do see this. That means the refrigerant's leaving the condenser too fast, and it's overfilling the evaporator coil. That one, we're looking at our metering device. The metering device is either stuck open or too big. With a fixed Orfice, I find many times people put the wrong metering device. The metering device should match the compressor. And I see a lot of times people will replace the compressor or the outdoor unit and they don't put the matching metering device in. And it works-ish, but it doesn't work like it's supposed to. And end up with a flooded evaporator coil and a starved condensing coil. So it's letting too much refrigerant flow through. On a TXV, I've seen it oversized, but typically on a TXV, you'll have a problem as they didn't braze with nitrogen. And because they didn't braze with nitrogen, they ended up with that TXV being stuck in the open position, and more likely than that, the sensing bulb. For some reason, people don't understand how that sensing bulb works, and they think if they take the sensing bulb off, they'll have more cooling. So I guess they think it's just magical unicorn juice, and by putting more magical unicorn juice in the evaporator, it makes more cooling, but it doesn't work that way. That sensing bulb needs to be attached to the suction line. And if there's a problem with the unit and it's not adjustable or something's not changing, then you replace that metering device. But taking that sensing bulb off into the air, I see it many times, have to reattach it, adjust the TXV, the system works beautiful after that. So these are things to think about though. Understanding starved, good, or flooded evaporator and starved, good, or flooded condenser just simplifies that. So having these little notes, high superheat's a starved evaporator, plus or minus 3 is good, low superheat, a flooded evaporator. And on the other side, we could see high subcooling, a flooded condenser, plus or minus 3, a good condenser, and low subcooling, a starved condenser. Just simplifies everything, makes it a whole lot easier. So this is our basics of refrigeration cycle. Now, if you're not getting all this, it's okay. The idea is that you study it, you see it, the more that you see it, the easier it comes to you. But these are all the things, the little pieces that make this cycle work. A lot of people have gone through the whole career not understanding how this works. But the idea is that if you understand how the system's working, you're able to solve more problems and move up faster. What I want is for all of you to be successful. I want you to go out and make these big, awesome things, make changes in your life, solve big problems, understand more stuff, and be able to explain stuff to me. I want you to grow and be unlimited and change your life. That's what I want. That's why I'm spending all this time here, because I want you to have a great life. HVAC's been great for me, and it's changed my life. You need to know that if I can do this, you can absolutely do this. I have learning disabilities where I have really hard time struggling and focusing on stuff. Things distract me and I'm trying to do 2 things at once. I get frustrated and it's very difficult. It gets very frustrating sometimes, but I can overcome that. The dyslexia issue, getting numbers mixed up all the time. I didn't even know that was a thing until later in life. Really was a struggle. How I learn is a little different. I have to really push through reading stuff. The dyslexia is a big issue, so pushing through and making it happen. If I can do this, I know that you can do this. It takes practice. It's how much do you want it? Do you have that goal? Remember the goals? Are you looking at those goals? Are you trying to achieve this? The more that you apply into this, the more that you decide you want to be a thermodynamic expert, that's going to be that thing that pushes you to that next level. You get to decide how much you want to know, how much you want to learn. I just want to help provide just some of the tools to help get you that next step. There's so much beyond me that you're going to be able to learn. But ideally, these steps will help you go to that next level. Sometimes it's going to be frustrating. That's okay. Sometimes you want to give up. That's not okay. You got to push through. You got to stay with it. Stay at those goals. Stay focused on what you want to be. Review, see it again, rewrite it, verbally say stuff out loud. Whatever it takes to make sure you get this information, that's what's important. And if you don't get every detail, it's okay. The concept is what I want you to understand more than anything. The concept is most important. And remember, number 1, know the answer. That's perfect. But number 2, know where to find the answer. You can't remember everything all the time, but you can find the answer. So if you make these notes and what's happening, then you can go back and reference it. Man, I can't remember what that should be. Oh, I can't remember what started and flooded was. You can go back to these notes and you can reference these notes, and they're there to help you. These are tools to help you understand that whole entire system. But the more you know, the more you can do. It just simply unlocks more doors. Never stop learning and stay at it. Next, we're going to take and apply different scenarios to this refrigeration cycle. If we change this, what would happen to all these other numbers? It's going to be really cool, exciting. I think so. Hopefully you enjoy it too. Stay tuned for the next video.